So I want to continue the discussion from yesterday, but what I'll focus on in today's talk is not so much the long-time behavior of solutions of Navier-Stokes, but rather how one can sort of modify the point vortex model that we've heard so much about this week to incorporate the effects of viscosity and finite core size. Because, of course, we've heard actually very beautiful results about how one can use solutions of the point vortex model to approximate solutions of Euler's equation. It's not so natural if you're interested in Navier-Stokes rather than Euler, because, of course, the viscosity will instantly sort of regularize the point vortices. And so I'd like to talk about some ideas about how one can more or less systematically incorporate the effects of viscosity and finite core size into the model. And so this represents work with Althea Barbaro. It's a typo. I'm sorry, it should be Barbaro, Ray Nagum, Guido Sandri, and David Uminsky. So, and it appeared in these two papers. So I want to start out by returning to something that I did talk about yesterday, and that's a comparison between the two-dimensional vorticity equation written in terms of its original variables and what I referred to as the rescaled variables form of the two-dimensional vorticity equation. So remember, we introduced these new variables for space and time. So xi is this rescaled spatial variable, tau is this rescaled time variable. And when we rewrote the two-dimensional vorticity equation in terms of these variables, we found that really the only thing that changed was the form of the linear operator. Instead of just having nu times the Laplacian of W, we have nu times this new linear operator L. And I mentioned that L has certain sort of special properties which make it particularly convenient for studying the long-time behavior of solutions. And I want to return and explain some of those properties in more detail because they suggest a kind of natural set of basis functions with which to sort of reinterpret the point vortex model. So I'm going to set nu equal to 1 for convenience. We can always do that. Since we're in the whole plane, we can rescale the spatial variable xi to make nu equal to 1, so there's no loss of generality here. And I want to begin by just focusing on the spectrum of the operator L. So note that if we're in the original variables, the linear operator is just nu times the Laplacian, so the spectrum will be the entire negative real axis. So all points up to and including 0 will be in the spectrum of the linear part. And we'll see that the spectrum of L is quite different, and that will help us identify modes that are particularly associated with the long-time behavior of the solution. So how do we find the spectrum of L? Well, let's start by just looking at the eigenvalue equation for L, which is here. We can separate variables, so you get a pair of ordinary differential equations, one for the first component and one for the second component of psi. And if you rewrite this eigenvalue equation in Fourier variables, you get this simple first-order equation in K, and that's, of course, an equation we can solve using integrating factors. The solution is written there. Here, h is the Heaviside function, the function that is 0 if its argument is negative and 1 if its argument is positive. And the form of the solution is a little bit surprising at first sight, maybe because there are two undetermined constants. This is a first-order equation. We have two undetermined constants in the solution, and that's, of course, just a reflection of the fact that this equation is singular at k equals 0. Okay? Now, we've solved the eigenvalue equation for every complex number lambda. Okay, there's the solution. So is every point in the spectrum of this operator L? Well, the answer is no. But the reason is, of course, that we really need to ask ourselves, on what function space are we trying to compute the solution? Because when the real part of lambda is positive, these putative eigenfunctions blow up at k equals 0, and so they're not in a sort of nice function space. So we're going to choose a very special class of function spaces to work in, and these are these weighted L2 spaces that I mentioned yesterday. Okay, so recall that L2 of M is just square integrable functions which remain square integrable when multiplied by this weight function that grows like psi to the m. And you can, in an entirely analogous fashion, define weighted Sobolev spaces, which just require that not only f, but the derivatives of f of order less than or equal to s are also integrable with respect to this weight. So why are these spaces particularly nice? Well, these spaces are nice because I've got my eigenfunction written in terms of its Fourier transform, and Fourier transform acts in an extremely nice way on these weighted spaces. A function is in the Sobolev space, the weighted Sobolev space HSM, if and only if its Fourier transform is in the space with the indices interchange. So the weight becomes the smoothness, and the smoothness becomes the weight. And this is, of course, just because Fourier transformation turns multiplication into differentiation and vice versa. Okay. So now we can talk about whether or not this supposed eigenfunction is actually in the function spaces that we want to work on. Note that away from the origin, these functions are extremely smooth and extremely rapidly decaying. So the only possible impediment to this being an eigenfunction occurs at the origin. And so the question is just, well, is this function and its derivatives, are they actually square integrable in some neighborhood of the origin? If they are, then this will be a perfectly good element of this weighted Sobolev space, and the corresponding value of lambda will be a point in the spectrum of our rescaled operator L. So the first thing to note is that there are certain special values of lambda. So if lambda is any negative half integer, then you can choose the constants. They suddenly became a plus and minus instead of c plus and minus. I don't know why that happened. But you can choose those constants so that, in fact, these two terms combine, and we just get some power of k times an integral power of k times the Gaussian. And so for any values of the indices m and s, the complex numbers lambda, which are negative half integers or non-positive half integers, are eigenvalues of this operator L, and the eigenfunctions have extremely simple Fourier transforms. On the other hand, so in particular, the one I want to call your attention to, because it'll come up again and again, is something we saw played a very important role in the dynamics yesterday, and that's just the case when lambda is equal to 0, the eigenfunction corresponding to the eigenvalue lambda equals 0 of this operator is just the Gaussian. Okay. On the other hand, for the values of lambda that are not negative half integers, you can check, and there are no choices of those constants which make the resulting function smooth, and hence for at least some values of s, the corresponding function will not be in our function space. And what you can check is, for instance, that if you're in one dimension, there's no value of lambda with non-negative real part other than 0, for which the this function phi hat of lambda will be in this weighted Sobolev space. So more precisely, you can check, and you see that we have the spectral picture that I described very briefly yesterday. Namely, we have this distinguished set of points, non-positive half integers, for which we have explicitly computable eigenfunctions. In 2 dimensions, the origin is a simple eigenvalue with eigenfunction equal to the Gaussian, and these are multiple but explicitly computable eigenfunctions for all the other negative half integers. And then there is this half plane of essential spectrum, which, again, as I mentioned yesterday, we can push arbitrarily far to the left by choosing the weight in our function space appropriately. The faster the decay of the functions in our Hilbert space, the further into the left half plane the essential spectrum is pushed. And that suggests really that if we're interested in long-time behavior, it ought to be the modes that correspond to these isolated eigenvalues that are really responsible for determining the asymptotics. Okay. And so this calculation was first done by Gallet and Rogel in 1 dimension in the context of sort of dissipative wave equations, and then Thierry and I extended it to general dimensions for later. So as I said, if we are interested in the long-time dynamics, then it's very suggestive from, at least if you think about the problem from a dynamical systems point of view, that the most relevant modes should be those corresponding to these isolated eigenvalues. In order to compute the projection onto those modes, we need to understand the eigenfunctions of the adjoint operator, which you can check is very closely related to L itself. We just change the sign and reverse the order of the operations in that second term. And again, you can write out the eigenvalue equation for this adjoint operator. And now we see we get an even simpler eigenvalue equation, because this is, of course, just Hermite's equation. So the adjoint eigenfunctions will just be the Hermite polynomials. Okay, so if you want to compute the long-time asymptotics, we can work with the eigenfunctions associated with the eigenvalues minus n over 2. And since I'll be referring to this again and again, let me write it up here. Remember that the eigenvalue 0 had eigenfunction just equal to the Gaussian. The eigenfunctions corresponding to the other eigenvalues were given by powers of k times the Gaussian. But of course, when we revert from the Fourier transform variables to the original variables, those powers of k just become derivatives of the Gaussian. So the eigenfunctions are given just by derivatives of the Gaussian. So Hermite functions, if you come to this from quantum mechanics. And the projection onto the eigendirections is just given by integration with the Hermite polynomials. Okay? And there's some normalization factor here in front of the integral. Okay, so as I say, there's also this half plane of essential spectrum, but I'm just going to keep pushing it further and further to the left. Okay. So while my principal emphasis in this lecture is going to be sort of extending the point vortex model, I want to just point out that one can also use the picture we've just drawn to analyze theoretically at least what happens to small solutions of the two-dimensional vorticity equation. Because, again, if you think about this spectral picture from a dynamical systems point of view, you would expect that there would be invariant manifolds in the phase space of the full nonlinear equation that, at least near the origin, were tangent to the eigenspaces given by these exposed eigenvalues. And indeed, that is the case. So this is, again, work of Gallet and myself. So if you take the weight parameter in your function space to be bigger than 3, then you see that there are 2 eigenvalues that extend beyond the essential spectrum. the zero eigenvalue is a simple eigenvalue, minus a half is a double eigenvalue, and you can construct a three-dimensional invariant manifold tangent to the eigenspace of these eigenvalues and show that any small solution of the full two-dimensional vorticity equation, at least in the rescaled variables, will converge at a rate of e to the minus mu. This should be tau. I'm sorry, this is the rescaled variables, e to the minus mu tau, for some mu greater than a half. So all the long-time behavior up to corrections of this order can be obtained just by studying the three-dimensional system of ordinary differential equations that results from restricting the vorticity equation to this three-dimensional manifold. And and then one can develop normal forms for the equation near the origin, and all of the machinery of dynamical systems can come into play here. And now, just to connect with Idris's question from yesterday, if one works not on all of R2, but instead on a finite domain with periodic boundary conditions, a rectangular domain with periodic boundary conditions, this is quite reminiscent of the results of Foyash and So, who made a similar construction for that finite dimensional situation. But I want to point out that there's mathematically a sort of significant difference. If you're in the bounded domain with periodic boundary conditions, then you can work directly with the equation in its unscaled form, because there the eigenvalues of the Laplacian are discrete from the beginning. You don't have to deal with this problem of essential spectrum extending up to the origin, whereas it seems that if you're on an unbounded domain, it's much more natural to work in terms of these rescaled variables, because that helps you identify the modes that are most responsible for the long-time behavior. So now I want to sort of move a bit away from the theory and just suggest how we could use these eigenfunctions that we've just computed, namely the Gaussian associated with the zero eigenfunction and the derivatives of the Gaussian associated with the higher eigenvalues. So how we can use that to actually sort of compute solutions. And it turns out that for actually doing some computations, it's better to revert back to the unscaled variable. So I'll denote by psi the expression for this Gaussian back in our original variables. Okay, so I'll just undo this change of variables, but we'll recall and work with the fact that the long-time asymptotics is really dominated by the eigenfunctions associated with these discrete eigenvalues. So then, of course, it's immediate that if you take this Gaussian rewritten in terms of the original variables, it'll solve the vorticity equation in its original form. So note that I've also now, we had rescaled things so that the viscosity parameter was equal to 1. I've undone that rescaling as well, and so I'll include the viscosity explicitly in the eigenfunctions. And I've just normalized things so that the integral is 1. So we have then these higher eigenfunctions, which instead of being expressed in terms of derivatives of the Gaussian here, are just derivatives of the rescaled Gaussian, or the unrescaled Gaussian, so to speak. And the idea is that we'll now expand the solution of the vorticity equation in terms of these eigenfunctions. Okay? And of course, we'll have some time-dependent coefficients in that expansion. And so how do we compute the coefficients, and does this expansion converge? So those are the two obvious questions at this point. Well, computing the coefficients is very straightforward. We saw earlier that the projection onto the eigenfunctions of this rescaled operator were just given by the integration with respect to the Hermite polynomials. And if we now include if we undo the scaling variables in the Hermite polynomials, we find that they can be rewritten in terms of this generating function. So just derivatives of, again, a Gaussian. That will be important for for our computations. And so the coefficients in the expansion are just given by integration with these sort of Hermite polynomials, but including this time-dependent factor, lambda. As for the convergence, I won't go into the details, but it turns out that indeed this expansion does converge, provided we restrict our attention to rapidly decaying vorticity distribution. So in particular, suppose that the initial vorticity distribution decays sufficiently rapidly that when you square it and divide by the Gaussian, that result is integrable. Okay, so we're looking at very localized vorticity distributions, sufficiently localized that you can multiply them by a Gaussian and they're still integrable. But if you begin with such a vorticity distribution, then the series will converge. And the reason that occurs is that you can rewrite this operator L in a sort of extremely weighted L2 space, a weighted L2 space in which you take a weight that's like a square root of a Gaussian instead of a polynomial weight. And in this weighted space, this operator actually becomes self-adjoint, and so its eigenvalues are automatically a complete set in this space. So we do have convergence in this space of rapidly decaying functions. And what's more, you can show that if the vorticity distribution decays sufficiently rapidly at time 0, that this integral is finite. It will remain finite for all subsequent times, though it'll typically grow, and hence this expansion in terms of the eigenfunctions of the rescaled operator will be convergent for all times t. So I should make just one remark here. We had these discrete eigenvalues, but then we did have this half plane of essential spectrum. So what has happened to it? Well, as I said, by taking higher and higher polynomial weights, you could push it farther and farther into the left half plane. By taking this Gaussian weight, we've just pushed it completely out of the picture. So for these very, very rapidly decaying vorticity distributions, the essential spectrum has just disappeared. So, the other remark I want to make is that we know explicitly what the velocity field associated with the Aussane vortex is. So that's the analog of this Gaussian vorticity distribution, written now in the velocity formulation. And since our eigenfunctions, the eigenfunctions corresponding to higher eigenvalues are just derivatives of the Gaussian, you can show that the derivatives associated with the higher, or the velocity fields associated with the eigenfunction psi k1, k2 can just be obtained by differentiating this expression. Okay, and so this is just a straightforward calculation with the Biot-Savart law. So we have sort of rather explicit expressions for both the velocity and vorticity fields associated to these discrete eigenvalues. I'm sorry? Oh, yeah, absolutely. Sorry, minus x2, x1. Thank you. Yep, absolutely right. Okay, so and so just as we expanded the vorticity field with respect to the eigenfunctions psi k1, k2, we can expand the velocity field with respect to these derivatives of the velocity field corresponding to the Aussane vortex. And now, so far this is all just expanding everything in sight. The thing that's sort of nice is that the coefficients, the MKs, the coefficients in this expansion turn out to satisfy relatively simple ordinary differential equations. And that's a consequence of the very nice sort of integration equalities one has for Hermite functions. So if we just take the formula for the vorticity expressed in terms of this expansion, wherever it went, in terms of this expansion in terms of these eigenfunctions psi k, just take this formula, insert it into the vorticity equation, and calculate a little bit, or maybe more than a little bit. You find this expression. So, and now if you use the projection operator, remember we discussed how you can project onto the eigenfunction psi k1, k2 by integrating with respect to their Hermite polynomial, then you find that you get this ordinary differential equation for the evolution of the k1, k2 coefficient in this expansion. It's a sum over products of other coefficients multiplied by this factor. So we project onto the k1, k2 direction the velocity field associated with the eigenstate L1, L2, dotted with the gradient of the eigenfunction k1, k2. Or I'm sorry, there's another typo. This should be M1, M2. Okay, so we have these coefficients expressed in terms of this projection, and what I will try to show a little later, if time permits, is that because of the properties, because these are all expressed in terms of Hermite functions, and because of the sort of known sort of integration formulas for the Hermite functions, there are actually rather simple combinatorial formulas for the coefficients in these equations. Okay? And so this is just a very simple numerical implementation. So what we did is we just looked at the solution of the vorticity equation with this simple initial vorticity distribution for different numbers of, including different numbers of moments. And so here the horizontal axis is the number of moments that we included in the approximation. And as you see, as the number of moments increases, the vertical axis is the logarithm of the error in the computation. As the number of moments increases, we get better and better approximation to the true solution. So that's how we can express a single vortex with respect to the eigenfunctions of this rescaled operator. But in fact, as we've seen on a number of talks this week, a typical fluid distribution doesn't consist of a single vortex, but rather a collection of different vortices. And the sort of Helmholtz-Kirchhoff model models this by assuming we have a lot of point vortices scattered through this fluid. And I'd like to explain now how we can extend the discussion that we've just had about representing a single vortex of the Navier-Stokes equation in terms of these eigenfunctions to a situation where we have multiple vortices spread throughout the fluid. So we'll take our initial vorticity distribution and we'll break it up as a sum of different pieces. Okay, and this is completely arbitrary how we do this. I mean, no one tells you even what number of pieces you ought to take. You can do this however you like. The only restriction we'll make is that we do require that each piece of the vorticity have non-zero circulation. So we don't, as we saw yesterday, even for analyzing the convergence to the Osane vortex, a vorticity distribution with circulation zero somehow is a little bit anomalous. So we want to avoid that. So break up this initial vorticity distribution however you like. Try to do it in a way that somehow reflects the nature of the flow. So if you see some sort of regions of localized vorticity in your initial data, then you should choose one of these patches to sort of overlap that piece of the domain. But just make sure that when you've done this decomposition, none of the pieces has zero circulation. And now, associated to each of these patches, we'll look at the center of vorticity. So we'll just take the integral of x times omega j and divide by this total vorticity. And the idea is we're now going to try to write the solution at some later time. So the solution of the vorticity equation at a later time will be written as sum of these n vortex pieces, which the vorticity distribution in each piece will evolve in some way, and they'll move around in some way. Okay? And again, you should think of this, I want to sort of argue that we should really be thinking of this as just somehow taking the point vortex equations, in which case each of these would just be a delta function, and allowing or somehow incorporating the effects of the dissipation in the equation. And of course the associated velocity field can be broken up in a similar fashion. So again, we have to figure out how all these quantities evolve. So we'll take the decomposition that we made here on the previous slide and insert it into the equation. A very simple calculation with the chain rule shows that you wind up with this equation. So I can rewrite that to focus on just the behavior of the jth vortex piece. And I get this PDE. So most of it looks quite natural. So we have this dissipative term. We have the nonlinear term, which gives us the interaction of this patch of vorticity with the effects of all the other patches. But then there's this additional term in the equation which is related to the motion of the center of the vortex. And so that's something we still have to decide. How do the centers of the vortices move? So if you think about the Helmholtz-Kirchhoff model, it's sort of intuitively, at least, clear that since the vortex is just concentrated at a point, it ought to respond by just being carried along by the velocity field induced by the other vortices. But now these vortex, I don't want to call them vortex patches because that means something else. These vortex blobs, they're spread out in space, so it's not so clear. How do you push each blob around? And so the choice we make, and this is again very much motivated by Gallais and my work, is that we'll require the vortices or the blobs, each blob, to move in such a way that the first moment of the vorticity vanishes at all times. Okay, so this is a sort of funny integral condition. Why do we choose that? Well, again, it goes back to the work I described briefly earlier on constructing invariant manifolds for the long time asymptotics of the solutions. And what emerged from that, although I didn't stress it here, is that that invariant manifold picture showed that if this condition on the first moments is satisfied, then one actually approaches the limiting vortex solution at a faster rate. Okay, and so somehow by enforcing this condition, we hope to be able to see each of these vortex blobs kind of approach their limiting form at a faster rate. So that's the motivation for choosing this condition to determine the motion of the centers of the blobs. Now, it's sort of easier to deal with this condition in differential form, so we can do that by just changing variables in this equation. So let z equal x minus xj. We get this condition, and now differentiate this condition with respect to time and insert the partial differential equation that was derived a few slides previously for the time evolution of the jth vortex blob, and then integrate by parts a lot. And what you find is that the differential equation for the motion of the jth vortex, so the position of the jth vortex will have two components, so I'm writing out each component here. So the first or second component is just given by this sum over the sort of average effect of the velocity field due to all the other vortices or all the other blobs acting on this jth blob. Okay, so we have a sort of averaged advection of the vortex blobs in this case. Okay, and so now we get some coupled system of ODEs and PDEs that describe the evolution of the vorticity. And so I want to see what the connection is with the point vortex model. So suppose that each of your blobs was just a point vortex. Of course, this won't happen because, as I said, the dissipative term in the equation will instantly regularize this delta function. But if somehow you could keep the jth blob as a delta function for all time, then its velocity field is this formula that we've again seen several times already this week. And if you just substitute these two expressions into the equations here, then you can evaluate those integrals, and you find that the equations of motion are exactly those of the Helmholtz-Kirchhoff model. So at least formally, this is some generalization of the Helmholtz-Kirchhoff point vortex equations. So now I want to sort of combine the two themes that I sort of had in this lecture. The first, what is actually the second theme, is that we can kind of naturally break up a given vorticity distribution into pieces, which we want to think of as representing the important regions of vorticity in the system. And we have a natural set of coupled PDEs and ODEs that describe both how the vorticity distribution in each blob evolves in time, and also how these blobs move around and interact with each other. And then we can, for each one of these vortex blobs, we can now expand it in terms of the eigenfunctions that I discussed earlier. So we'll represent each of these blobs in terms of these Hermite functions. Okay, and if we insert this expansion into the PDEs that described the evolution of each vortex blob, then we wind up with just a very large system of ODEs that describes how both the vorticity distribution in each blob evolves and how the centers of motion of each blob change. And so I won't write out that system of equations, but I'll just look at one very special case. I mean, you can write out the system of equations, and it's less awful than you might imagine. Again, because of the sort of nice properties of their Hermite functions. But I'm going to look at just a very, very simple example to try and illustrate what happens here. It's been observed for some time that if you start out with widely separated regions of vorticity, then the evolution of the flow for at least long but finite times can be well approximated by just replacing each blob of vorticity by a Gaussian. And so I want to look at... and by the way, that fact, which was first observed sort of numerically, was actually sort of proven rigorously to hold by Gallet in this relatively recent paper. So in our sort of moment expansion, if you like, approximating each vorticity blob by a Gaussian just corresponds to retaining only the first term in this infinite expansion. And so suppose we just take two vortex regions and make this Gaussian approximation to each vortex region, then we find that the equations for the moments are quite simple. The total vorticity, M super J, refers to the total vorticity, so that's just this coefficient. This is the total vorticity of each blob, and it doesn't change in time, and that's quite natural. And then the centers of the blobs move according to this system of equations. So the first component of the first vortex satisfies this differential equation. And then there are three other analogous equations that tell you how the other components of the first vortex and the two components of the second vortex move. Okay, and so now what I would like to do is try to explain how to compute the right-hand side here. Because I think it'll sort of illustrate why I made this remark that the system of equations that you get for the evolution of these the centers of these vortices and also the evolution of their coefficients are not so bad once you use what you know about their Hermite function. So how does this equation come about? Well, remember what we said is that the first vortex should be advected by this sort of average effect of the second vortex on the first vortex. So what's that going to be? Well, as was just discussed, we can express the velocity field as sort of this kind of perpendicular gradient or twisted gradient of some stream function. And the stream function, of course, is just given by minus the Laplacian of the stream function is the vorticity. And so we'll express the velocity field associated with the second vortex blob symbolically, just as we take the inverse Laplacian of the associated vorticity distribution and then just apply this twisted gradient to it. Okay? So why does that help? And so here you should think of this, this inverse Laplacian is just integration with respect to the Biot-Savart kernel. Okay, that's what I mean by that. So we get the the velocity field associated to the second vortex blob is just going to be given by the Gaussian vorticity distribution. Remember, we're assuming that both vortices are approximated by Gaussians, and then we apply the inverse Laplacian and then this sort of twisted gradient. And there's one thing that I want to stress here. You would ordinarily take these derivatives with respect to the variable x, but we can equally well, thanks to the chain rule, take the derivatives with respect to the variable corresponding to the separation between the two vortices. And so then this integral, which tells us how the vortex is advected, if we insert this representation for the velocity field into the integral, then we can pull the action of the inverse Laplacian and the gradient out of the integral. It's an integral with respect to x. And now we're left simply with the integral of the product of two Gaussians. And that's something that is extremely easy to compute and is itself a Gaussian in terms of s. So the result of performing this integral is a Gaussian in terms of x. And what's this operation? Well, this operation really is just saying, take a given vorticity distribution and find the velocity field associated with it. And so after we do this integral, we have a Gaussian, as I said, a Gaussian in S, and this just says find the associated velocity field. And so that's how this term arises. This, of course, you recognize is just the velocity field associated with a Gaussian vorticity potential. Okay. So that's and sort of analogs of that calculation apply then to more complicated coefficients in this equation. So one can generate the equations that describe the motion of these vortices in a very straightforward fashion using properties of these Hermite functions. So if we now look at the equations we derived for that situation where we approximated our two vortices by a pair of Gaussians, then as we heard on a number of occasions this week, if you take a pair of point vortices of the same sign and strength, and they will just rotate around one another with constant velocity, you can solve those ordinary differential equations that I wrote down a couple of slides ago. In this case as well, you again find that the two vortices rotate around each other on a circle of fixed radius, but now they slow down with time. Remember, lambda of t is growing linearly with time, and so we find that the rate of rotation slows down with time. So this is one effect of viscosity that emerges even in this very simple circumstance. The other thing you can see, and again this sort of reinforces the relationship with the point vortex model, if you take the viscosity to 0 And if you take lambda naught, which just describes the size of the core of the original vortex, if you take those two parameters to 0, then you find that the rotation rate converges to just 2m over 2 pi d squared, which is, again, exactly the rotation rate you obtain for a pair of vortices in the Helmholtz-Kirchhoff model. So again, we recover the Helmholtz-Kirchhoff result in the appropriate limit. So the other thing you can do, so as I said, you can sort of break up your vorticity distribution pretty much however you like. So if you have a plus vortex there and another plus vortex there, it sort of makes sense that you would maybe break that vorticity distribution into two pieces and represent each one by a Gaussian. But nobody says you have to do that. If you want it to be a little bit contrary, you could say that's actually just one vortex, but it has some higher moments besides the Gaussian. So we actually looked at what happens. Suppose you approximate that not as two Gaussian vortices, but as one vortex of higher with higher moments, and then again it just sort of rotates around. The speed is slightly different, but not so different. So here, I think I've forgotten now. I think the dashed line corresponds to approximating this by two Gaussian vortices, and the solid line corresponds to approximating this by a single vortex, but with higher order moments. And so either way, one gets actually quite consistent approximation to the rotation of this pair. So, and that was work of Ray Nagum, Guido Sandri, and David Uminsky, who used our model to approximate this situation. So, and so just to wrap up today's lecture, I would like to sort of argue that these Hermite functions, which emerge very naturally as the eigenfunctions of the linearized vorticity equation when we work in terms of these scaling variables, these seem to be very convenient variables with respect to which to study long-time asymptotics, not just of the vorticity equation, but in fact of a really wide variety of sort of parabolic type equations. From a theoretical point of view, they allow us to construct these invariant manifolds which govern the long-time asymptotics of solutions. And they also give a kind of natural way in which to extend the Helmholtz-Kirchhoff point vortex model to incorporate the effects of viscosity and finite core size. So that's all I wanted to say today. Thanks very much.